Hey, chemistry. Hope you guys are doing well today. We're going to talk about mole ratios today. So we're revisiting conversion factors. We're staying with this whole concept of trying to make a measurement in one unit and converting it into another unit. Same measurement, different unit, right? So we've been dealing with this conversion through our new favorite skill of dimensional analysis. And I'm going to show you another conversion factor that we can use. But before we get to this new conversion factor, I want to talk about the conversion factors that we've dealt with so far. So we talked about a lot of them, but 3 or 4 of them specifically center around the mole. And I don't know if you realized this, but those 4 that all center around the mole are all talking about the same thing, the same particle, right? So if we know that we have 1 mole of carbon dioxide, I can say the mass of that molecule. But we're still talking about carbon dioxide, right? So I would write, let's see, 16 plus 16 plus 12.01 would be 44.01 grams of carbon dioxide. So that's my conversion factor. I can convert from moles of carbon dioxide to grams of carbon dioxide. And I would write that as a fraction. 1 mole of carbon dioxide over 44.01 grams of carbon dioxide, or the opposite, 44 grams of carbon dioxide over 1 mole of carbon dioxide. But the point is, they both have to do with carbon dioxide, right? We can do the same thing for moles to particles. In this case, carbon dioxide, the molecule, so I'm going moles to molecules. 1 mole of carbon dioxide is equal to 6.02 times 10 to the 23rd molecules of carbon dioxide. And then similarly, we can go from moles of carbon dioxide to liters of a gas, or if we're dealing with an aqueous solution, we can also go to liters of solution, and that would be molarity, right? But in this case, carbon dioxide is a gas. So I would go from 1 mole of carbon dioxide to 22.4 liters of carbon dioxide. So this is what I'm talking about. All of these conversion factors we've talked about that are dealing with the mole, are based in the mole. They are consistent with the thing that I'm talking about. They must be consistent with the thing that I am talking about. If I write something like 1 mole of carbon dioxide equals 18 grams of water, that is not a true statement. Those two things are not equivalent. If I have a mole of carbon dioxide in some container on this side, and I have 18 grams of water in some container on my other side, those two things are not the same amount. They're not the same amount of mass. They're not the same amount of molecules of carbon dioxide or molecules of water. They're not equivalent. So I can't make a statement like this because it's not true. It doesn't turn into a conversion factor where the top is equal to the bottom, right? And that's one of our necessary things to check off about our equivalent statements. And so how do I convert from carbon dioxide to water? That's the question of the day. And this is something that's really practical in chemistry, and it's also really practical in real life. Let's say, for example, that I'm making pancakes, which I love to do. I don't make pancakes this way, but I do love to make pancakes. Okay, so let's say I want to make pancakes, right? And I want to make pancakes for as many people as I possibly can. And I have a whole container of eggs. In fact, I have 18 eggs. I don't even have a dozen eggs. I have 18 eggs. So the question would be, how many pancakes can I make, right? This is a very practical question. We run into this all the time. If you bake, if you work anything hands-on, whether that's like building with wood or scrapbooking or working with like dimensions inside Photoshop with a camera. I mean, it's all over the place. If you're a welder, if you're an electrician, if you're a doctor, if you're a lawyer, you're gonna deal with these like scale ups and scale downs, right? So, again, you know how to do this with proportions. I want to take us today into being able to do this in dimensional analysis so then we can utilize this whole set of conversions, as well as going through in between two things like eggs and pancakes that are not related. Right? Okay, so that's where we're going today. Possibly the most practical skill you will gain from chemistry, from the entire year of chemistry we are getting into today. So let's take a look at this, shall we? Notice that on here, on our little chart as it stands, I don't have this conversion, right? This is moles of A, this is grams of A, this is liters of gas A, or liters of solution A, and this is particles of A. I have no B. That's what we need to add today. Where's our B? All right, so if I'm dealing with, let's go back to this eggs to pancakes problem. Again, we're going to start super simple so we can gain this skill of dimensional analysis in a really simple context that we can already understand before we put the skill into a context that's much harder to visualize, like atoms and molecules. So if I have 18 eggs and I want to convert to pancakes, we're going to set it up exactly the same. We have our given or our measured amount that's specific to this problem. Not every day will I find myself with 18 eggs, right? Some days I may find myself with 3 eggs. Some days I might find myself with 1 egg, but today I happen to find myself with 18 eggs. This amount is specific to my context right now that I'm dealing with, right? We're going to multiply it by a conversion factor. This is the relationship between the two things that I'm trying to deal with, eggs and pancakes. Remember, this is consistent. This is a consistent ratio that should be true always, or at least no matter what day I find myself making this recipe. Right? Okay, so we're going to set it up exactly the same. Let our units lead us through the problem. So if eggs are on top, we put eggs on bottom. I'm trying to find pancakes, so I'm going to put pancakes on the top here. And now this is my determined ratio that is going to be true every single time that I sit down and I make this recipe. So it takes 2 eggs to make 5 pancakes. So now I can go ahead and calculate 5 times 18 divided by 2 gives me 45. That's a good pancake day. If I have 18 eggs, I can make 45 pancakes. Sounds like a good morning. All right, now some people take issue with this and they say, But you can't just make pancakes out of eggs. You can't make pancakes out of eggs alone, right? You also need flour and you also need baking powder. So where are those things? They're missing. You just looked at eggs, right? Well, you're right. You can't make pancakes from just eggs. So when we're doing these calculations, usually in the problem, what they're going to say is something like you have as much flour and baking powder as you need. You have storehouses and storehouses of flour and baking powder. So along with this comes an assumption. Flour plus baking powder, or whatever your other reactants are, will not run out. You have as much of that as you need. So you don't have to pay attention to how many pancakes you can make from the flour and the baking powder, because eggs is the first thing that's going to run out. Okay, now let's take a minute. I told you we were talking about conversion factors today, right? So let's take a minute and look at our conversion factor that we just made. Okay, so let's evaluate this in terms of our conversion factors. First of all, do I have 2 units? Yeah, I do. I have eggs and pancakes. I have 2 units. Check. Is the top equal to the bottom? So if I have 2 eggs in this hand and I have 5 pancakes in this hand, I don't have the same thing in both hands, right? So they're not equal, but they are equivalent. In this reaction, in this recipe, if I use 2 eggs and whatever else I need, I can make 5 pancakes. Those 2 things are equivalent. So I can write a true equivalent statement. 2 eggs, assuming that I have enough of everything else that I need, equals 5 pancakes. These 2 things are equivalent, right? It's the same thing that we talked about earlier, like in one class of mine, for example, I have 16 women, right? So let's say I have a full classroom, and in my one class, I have 16 women. Now, if I hold one class in my hand and I hold 16 women in my hand, are those 2 things equal? No, but they are equivalent, right? If I'm talking about those 16 women, then I'm talking about my class. If I'm talking about those 16 women and the men involved in my class, I am describing one class. So those 2 things are equivalent and they can be used as a conversion factor. So let's go back and look at this recipe a little more closely. What are some other conversion factors that I can write? Pause the video here and see how many conversion factors you can write. 1 cup of flour. I can write 5 pancakes. 1 cup of flour is equivalent to 2 eggs in this recipe. 1 cup of flour is equivalent to half a teaspoon of baking powder. So just looking at flour and the relationship of flour to all of these things, I can write 3 different conversion factors, and I can flip all of those, right? If I need pancakes on the top and flour on the bottom, that's legal to do. I can flip those. I can flip all of these. So really, I can write 6. Now, I could go ahead and do that with everything else. 2 eggs. We already have its relationship to flour. Let's write out its relationship to baking powder. 2 eggs and its relationship to pancakes. How about baking powder? 0.5 baking powder. I already have its relationship to flour, to eggs, but I need its relationship to pancakes. And then pancakes relationship is here, flour, eggs, baking powder. So from this reaction where I have 3 reactants and 1 product, I can write 6 different conversion factors, and I can flip them. So really I have 12 different conversion factors. So you can use any relationship. You can use a relationship of reactant to reactant, right? Flour to eggs. You can use a relationship of reactant to product, like flour to pancakes. If we had another product here, you could write a relationship of product to product. So you can use any 2 things in a balanced chemical equation or a recipe to write these conversion factors. So now let's look at this in terms of a chemical reaction. Okay, so here's a reaction. It's N2 plus H2 goes to NH3, and it must be balanced. There we go. So there's our reaction. It's just like a recipe. I can do the exact same thing, right? So I can write a ratio that tells me if I use 1 mole of N2, I am going to also use 3 moles of H2, right? Now, this is a conversion factor. The top is equivalent to the bottom for this recipe or for this reaction. So as long as I'm in this reaction, I can use this relationship between nitrogen and hydrogen. If I change the reaction, my conversion factors are going to change. So these conversion factors are specific to one reaction. If you change the reaction, you're going to change your conversion factors also. Notice you can have a relationship of molecules to molecules. You can have a relationship of moles to moles, right? If I have 1 molecule to 3 molecules, I'm going to have 1 mole to 3 moles. So you can communicate this relationship or these conversion factors in molecules or moles. What other conversion factors can you write that deal with nitrogen? Pause the video here and see what you come up with. So we already have the relationship of nitrogen to hydrogen. We can also write a relationship of nitrogen to NH3. So that would be a 1 to 2 ratio. That's another conversion factor, and I can flip all of them. Now, one note here, just because I have a conversion factor doesn't mean that I actually have 1 mole of nitrogen or 3 moles of hydrogen. I might not, right? I might be dealing with blimps that we don't fill with hydrogen anymore, but they used to. They used to fill blimps with hydrogen. It turned out very badly. We don't do that anymore, but let's say we did. Let's say we're filling a blimp with hydrogen, and I am going to use 150 moles of H2. I don't know if that's reasonable or not, but let's pretend it is, right? Notice I have 150 moles of H2. I don't have 3. This conversion factor, remember, is the relationship that's always true. It's the consistent relationship. This 150 is my measured number or my given number or my number that's specific to this experiment only. And if I want to know, okay, I'm going to take my blimp filled with hydrogen because it's a terrible idea to fill blimps with hydrogen. I'm going to give it to a factory and allow that factory to use it to make NH3 or ammonia. So how much ammonia can I make with this much hydrogen? Well, we can now figure that out. We can convert from moles of hydrogen to moles of NH3 using the ratios 1 to 3 to 2 in my reaction. Now, I'm going to assume that I have as much nitrogen as I need. So I'm just looking at hydrogen's relationship to NH3, 3 hydrogen to 2 NH3, and I can take my calculator and figure that out. 150 times 2 divided by 3 gives me 100. Notice my moles of hydrogen reduce out. I'm left with moles of NH3. I ran out of space, so I'm going to write it down below. Equals 100 moles of ammonia. I can take my blimp to the ammonia factory and use it to make 100 moles of ammonia. So this mole to mole ratio becomes very useful. Notice it gives us a bridge here between moles of A, which in that last example was hydrogen, 2 moles of B, which in that last example was NH3. And now that conversion factor comes from a balanced reaction. And now that I'm in ammonia, I can figure out all kinds of things. I can figure out how many ammonia molecules I have, how much that ammonia would weigh, how many liters of ammonia I would come out with if ammonia was a gas, right? I now have a bridge between the two sides, and I can figure out a lot. Notice I could even go from grams of hydrogen to moles of hydrogen to moles of ammonia to grams of ammonia, right? It opens up my possibility. So we'll look at those possibilities another day. But for today, let me know what questions you have on this brand new and lovely ratio between moles of one thing to moles of something else. Let me know what questions you have. I'll see you in class.